Everyone, my name is Victor Hugo Germano, and I'm here today presenting my capstone project, Audio Adversarial Attacks on OpenAIWhisper. This is the capstone project presentation for the master's program on applied artificial intelligence at the University of San Diego. I start my presentation with a question. Can we trust LLM transcription as tools like OpenAIWhisper, a transformer-based automated speech recognition, are integrated in systems like the interactions between doctor and patients or voice-based command execution, it is important to understand how far these models can be affected by interferences, being that general noise or design sounds. Whisper is one of the most capable open speech recognition models available today. OpenAI trained it on 680,000 hours of audio, and it handles accents, background noise, and low quality recordings remarkably well. But there is a question that still remains. What if the interference that is added to an audio clip is not random? What happens when it is designed to fool the model? If you can, for example, take an audio file at a small perturbation, something that sounds like a static, and the model produces a completely wrong transcription, this is a real security vulnerability. And if we can define a specific output phrase from a transcription process, then it becomes even more dangerous attack vector, especially as transcription systems are fed into LLM pipelines and agentic workflows. This project tested the vulnerability with 4 different attack strategies, progressing from the simplest to the most challenging ones. The aim is to reach a 35 to 45 decibels signal to noise ratio, which becomes completely imperceptible to humans. And I believe that these transcription systems are only reliable as we can assert their accuracy in real life situations. So let me quickly explain what the Whisper architecture is. So specifically because this architecture, this attack is possible. Whisper takes a raw audio, converts into a MEL spectrogram, which is a 2D visual representation of the frequency content over time, and feeds that through a transformer encoder-decoder to produce the text tokens. The critical technical point is, in our implementation, the entire pipeline from raw audio to spectrogram is differentiable, which means that the gradients do not flow back to the audio perturbation that we needed to create. So we had to re-implement the MEL spectrogram computation in pure PyTorch so that we can support a gradient flow. That means that we can confidently compute which tiny changes in the raw audio would maximize the change in the model's output. And then we make the exact changes. This is the core idea behind all 4 attacks. So the 4 attacks that we implemented, they follow 4 specific families organized by 2 axes. One is per sample and universal per sample audio or applied to any type of audio. And another one is untargeted and that only affects the audio, and targeted attacks that we decide which phrase is going to be transcribed. So the first PGD, projected gradient descent, we create a some perturbation for a single audio clip, aims to disturb the result. The second, universal adversarial perturbation, we train a single fixed perturbation across audio samples. Once trained, the idea is that it works on any audio without re-optimization. We go for the targeted perturbations called Carlini-Wagner attack. Instead of just corrupting the output, we use a perturbation that forces the model to produce a specific phrase using the perturbation. And the last attack is the universal Carlini-Wagner. So we combine the universal approach with targeted injection. So a single pre-computed perturbation forces a result on any type of audio. Just explaining a bit more how this attack pipeline happens. So the audio comes in. We added a delta perturbation to the audio, and then we combine the signal passes through a differentiable MEL spectrogram. So we extract the MEL spectrogram features, and using the Whisper encoder decoder, we calculate the loss. Based on that loss, we backpropagate that to the and update delta, and only delta. We maintain the whisper weights completely unmodified and frozen. So with that process, we can generate audio perturbation that once added to a specific audio, it generates a specific result. For universal attacks, we just loop that process across thousands of samples. The result is a single perturbation file that can be applied to new audios at inference time. So at the end, what we're doing is we are exploiting a specific frequency beams in the whispers 80 beam Mel spectrogram uh, feature extraction. To a human, it sounds like faint static, but at higher SNR levels, the signal to noise ratio values, it would be imperceptible. Just let's just see how it works. So here, this is the adversarial speech attack demo example. So I'm going to record an audio, continue to talk just to show you how this attack works. Continue to talk just to show you how this attack works. So here I'm just running the clean transcript. As you can see, the left column and the right column, they do appear exactly the same. And I can choose for the universal untargeted attack and run the audio perturbation. And as you can see, the adversarial transcript now changes completely. And then we can see the result audio. Continue to talk just to show you how this attack works. So it feels like a specific static at the end and the beginning of the file. If we use the targeted Carlini-Wagner injection, and then it actually injects the phrase that we have, and then we can see how the audio behaves. Continue to talk just to show you how this attack works. So the interference is a lot higher, and we'll discuss that further in the presentation. So this is a live streaming demo. So as I continue to talk, because you're selected the attack type as clean, you're gonna see the transcripts do not change. As I change the untargeted universal adversarial perturbation, you see a slight change in the transcription on the right hand column, and as I use the targeted Carlini-Wagner injection, then the model behaves completely different. And in a way, because we're in a live stream, the way that I'm dealing with the buffering in order to generate a transcription also affects the results. But as you can see, the transcription results will keep adding the word website to the results. This is because the noise that we're using, it pulls the transcript results to the specific tokens generated by the phrase that we had. Okay, back to the presentation. So from the results that we can see from this this work, for the PGD, we achieved 92% success with audio with signal to ratio of 26.58. This is a per sample optimization. We can see that even the PGD and the Carlini-Wagner, which is per sample attacks, their success rate is much higher than the universal approach, especially because we can access those results much faster. But these results are not necessarily feasible in real world, because we would have to train a specific perturbation audio per result. The universal adversarial perturbation achieved a 60% success, but with a lower SNR, which is totally usable in real life situations. The universal Carlini-Wagner attack achieved a 58.6 success on the 350 validation samples at a signal to ratio of 11.35 decibels. These results are not necessarily great and do not achieve the expected 35 to 45 situations, but we believe that this is mostly because of resources constraints, the number of samples, and also the processing time. For the universal Carlin-Wagner attack, it took close to 10 hours of training to be able to achieve this result. So first, I believe we can attest that the whisper's robustness to natural noise do not extend to adversarial noise. Despite the massive pre-training that this open model had, the model has exploitable directions in the spectrogram space. Secondly, universality is the key to operational factor. That basically means that having a reusable perturbation that corrupts 60% of utterances or the audio clips is a viable jammer. Reusable perturbation that injects a chosen phrase with 58% of utterances is the potential prompt injection vector at the audio layer. And this is even before the text reaches the LLM. None of our attacks fully reach the ideal 35 to 45 decibels signal to ratio range for a truly imperceptible noise. The target attacks are mostly audible. As you can see, especially the Carlini-Wagner, this means that someone with access to the audio can understand that the audio is being altered. But the main vulnerability is on digital pipelines and batch transcription services. In the digital domain, batch transcriptions, API-based processing, phone recordings, this is a real risk. The perturbation can be embedded into audio files before they reach the LLM model. The main mitigation gap is imperceptibility. At 11 decibels SNR, anyone can see the noise is affecting the recording. One important aspect of this work is with the right development, I believe that this can help journalists, activists, and privacy advocates act as essential watchdogs against surveillance and rights violation. In the pursuit of promote data protection laws and protecting whistleblowers, this work can become a possible tool for investigative work and freedom of expression. I believe that the future work for this project lies within three specific themes. One is psychoacoustic mapping. The idea is to use perceptual models to hide perturbations in frequency ranges that humans cannot hear. The main approach here is this could reach a SNR at the imperceptible range. Lastly, the second attack vector would be over the air testing. Because of the time constraints, I could not test how these perturbations survive a physical playback through a speaker or recording through a microphone. This is also a possibility of future work. And third, we need to understand how those perturbations trained on a whisper-based model is the one that we used in this work, and also fool the whisper large or models like Wave2Vec 2.0. To conclude, I believe this work shows that whisper base can be corrupted per sample at 92% success and jammed at 60% universally. And we can also force a specific output or unseen sound samples. But the main takeaway from this work is it is possible to create a digital jammer using OpenAIWhisper. And the main trade-off for this work is the accuracy and audibility. Robustness to background noise does not carry over engineered sounds. And I believe that imperceptibility remains the biggest challenge. I'd like to thank you, and this is my presentation.